Yeah, why in this third question in the quiz, it asks what are the typical functions of device-independent part of iOS software, and it says that data encryption is not. But like, why is that? Because, for example, in Linux, there's a subsystem that looks, as far as I remember, and it does full disk encryption at device-independent way, but still it's uh, it's not visible to the software layer. So it's like it seems like this is a device independent of the software.
Because you're partially right, because it can be there as well. But from my perspective and for what I know, especially for the Macs, they have the encryption that is like built in into the hardware, like T2 chip.
Like the thing is that the actually encryption can be done in any level. There are disks that do disk level encryption.
Mm-hmm.
There are hardware that helps to do disk level encryption. There are software that does it in disk independent way, and actually is a software that does it at user software layer. For example, KeePass provides you encrypted storage of passwords at user software layer. This I don't know.
Okay.
Maybe it should be changed to something like
Sure.
it may be possible because
Okay, just you know that there is a process. Just write into the mistakes, so I will check it today and fix.
okay.
Okay. Okay. Any other questions? No questions. Did you enjoy the new version of the lecture? I mean, like when the video is uploaded up front and you just ask for questions.
Yeah, I certainly did. I don't know for others.
It seems like everybody else. I can go 5 seconds back. Yes, and you can go X2 if you want. It also helps. Yeah, so on the deadlocks, any questions on the lecture? Because this topic is very simple, I think. So you don't need to understand the very low level details. You just need to understand the approach, the four conditions, the three approaches or four approaches to handle them or not handle, and a few corner cases like live lock or starvation. And that's it. No questions? Okay. So, as usually, we solve the problems from Tannenbaum during the tutorial, so you can take your hands on, and that's it. By the way, you had a few of you had questions on Tannenbaum versus Bach and the alternative form of exam. Is there any questions still? No questions? So you covered this during the lecture, did you?
We didn't cover it.
I mean, some of you had questions. If you have still have a question, because there are like 20 something people who signed up for the alternative form of exam. No? Okay then. So let's go to the usual part. Is it possible that a resource deadlock, involves multiple units of one type and a single unit of another? It is a question to you and to you as well. Yes. Great answer. Why not? Can you provide an example? If you can come closer so they would hear you, I think would be like very good. Sorry, can you hear Vladimir?
No.
Mic check.
Right now, can you hear me? Or should I speak louder? Муахаха.
Okay.
This situation is definitely possible. Like in Tannenbaum, they had an example with process trying to acquire, for example, two printers.
Mhm.
It's great.
These are the resources, multiple resources at the same time and a single unit of another.
And it can ask for scanner, for example, I don't know.
So it doesn't really matter like right? How many types of resources you request. So you can even get blocked on a single resource of a
Yeah.
single type. So if you make a problem even harder with multiple resources of multiple types, why not? So as I said, the topic is rather simple. Do you guys agree? Do you have questions? Can you provide maybe other examples of how it is possible? So with the current example was from Tannenbaum with the printers and scanners. Yes, no?
I also can provide, like, for example, when we have a database and we need to print like some entries from database, initially we log database, then send some entries to printer.
So with databases, it is a bit. So you have you had the DNS course?
It's
Data-
usually for fundamentals of software engineering. Yeah, we manage first part.
So did you had the like MySQL, PostgreSQL, the connections to the database,
Kind of, yeah, kind of.
and transactions and logs? Kind of. Okay. So yes, the transactions and especially the rows in SQL-based databases is also can be a good example of a resource that can be blocked. Simple, trivial. So the solution that provided in the slides is yes, it is possible, and then the examples. So whatever. So the next problem. So first of all, do you guys remember what is a safe state? In terms of deadlock avoidance, deadlock prevent.
A safe state is a state from which there exist a series of scheduling actions that does not lead to deadlock.
Even if all of the processes will request all of the required resources, right?
Yeah.
So if, in plain words, is there a state, a combination of request allocation, resource allocations that will allow all the processes to complete, right? So this is a safe state. So again, there is an unsafe state in which there is no such a sequence that will allow all processes to finish. So to have, first of all, let us briefly repeat. What are the 4 conditions for the deadlock? Mutual exclusion,
Hold and wait.
hold and wait,
No preemption.
non-preemption.
Circular.
What is circular wait?
Process waits for event which can be
So you have like you have a process that requests another process that requests another process. So there's a thing called dependency graph in which you say which thing depends on which. And if there is a cycle, then there is a circular wait. Probably. It must not be always so, but if there is a possibility to have such a loop, then there is a possibility, there can be a condition in the system that will lead to a deadlock. So yes, so the next question is, among all of these 4 conditions, how many of them should hold to have a deadlock? All 4. So if of these 4 conditions, mutual exclusion, and circular, if 4 of them hold, then we have a deadlock. Then we have several approaches, exactly 4 in Tannenbaum, how we can deal with the deadlock. What were these approaches? Ostrich. Like Emo. Okay. Ostrich. So ostrich means
just ignore the problem.
yes, yeah. Put your hand in the sand. So you don't think about the problem. Why we mentioned it during the Kahoot? Because our usual operating systems, they do not care about deadlocks because it would be too much of overhead for them to detect it. So they say, okay, you are a programmer, you want to write software to run on our platform, so you handle it. We don't care, right? But of course, we should not say that this is the only way they do it. So all of the operating systems do ostrich, or macOS always does ostrich. No, it would not be true. Of course, as with processes, you have some abstraction, you have some understanding of what are the blocks, but every manufacturer will add something more from them. So again, I don't know, maybe now Apple has already introduced something to work with the deadlocks. It's possible. Right, so the ostrich, ostrich means do nothing. The next one is
Detect and correct.
so what is detect and recover? It's detect and recover, right? So you detect the deadlock somehow, and then you try to recover. What were the parts we mentioned for the recovery? There are 3 points. And what are the possibilities for the recovery?
Process termination and preemption of resources.
Yeah, so first,
Rollback.
let's move this. So the first one is preemption. What is preemption?
Rollback еще also.
The rollback and kill. So I want you to understand what is the preemption. It's like when you, with the force, take some resources from the process. So you don't kill the process, you just take resources from it.
Yes.
Okay. For example, as with the printer, can you try to give me some other examples of like any other resources that you can take from a process?
RAM.
RAM?
Like you can just force process to sleep, like smoke it out of memory, give this part of RAM to a known process.
You mean the physical RAM?
Yeah.
So you have smoking for it.
Yeah.
How it helps you to how the RAM of the process can be a resource for the deadlock. Maybe a shared memory that processes share. Maybe there is something, there is a lock or something that they acquired in on order. Like they say, they both said in the 2 processes, they said acquire lock 1, acquire lock 2, while they should do the opposite or vice versa. Right? Maybe database transactions or database roles. Something else. So something other than printers.
Specific that database transactions are
Database.
related with shared memory.
Yes.
Probably.
There's also a very interesting topic called distributed deadlocks. So maybe if we will have time, we will also cover, because it is very interesting because it requires to understand both what are the deadlocks and how to work with them in a system that is distributed, like you cannot see everything that is in the system. Because you have several machines, you might have a central master that commands all of them, or there is no master. This is like a federated network, and you don't know how to. You can when you cannot see the full system, how can you detect a deadlock? So it's an interesting area. So preemption: you take a resource from the process. The rollback is
We put checkpoints and we go to these points if we have a deadlock.
yeah. So how can you make a checkpoint?
Maybe for saving some state.
So like you create a snapshot of the whole process.
And not only the process, but all the
Resources assigned.
all the resources it uses and that stuff. So all the side effects. It's
So
quite a
does
difficult task.
it sound simple to you? I mean, to take a snapshot of the whole system, not of the whole system, but to take a snapshot of the printer, of the process, of the shared resources.
Well, it's not always possible because if, for example, a process is sending network packets, then the state of connection cannot be like snapshotted. But sometimes it is possible. So yeah.
So too many things can go wrong. But what can you? I think you really know one of the trivial examples of the rollbacks in the system.
Having log,
Databases.
same.
Transactions, right? So if transaction is not succeeded, it is rolled back. So they have some state, they try to apply the transaction, and if it's not committed, then it's rollback. A good example, I guess, like a smaller system, not operating system, but also a system that has this notion of rollback. Okay, and the kill is very trivial, I guess. So if it cannot succeed, we just kill it. See, kill cannot handle, just die. Okay. So this was the third one. Well, the second one. What was the third one? So we have the detect and recovery, and then we have
So can we try to prevent it?
avoidance.
Avoidance.
Let's check avoidance, because prevention is the topic is itself is not that hard, but prevention is very simple. Not very simple, but avoidance is more like dynamic. So what is avoidance? So you know there are four conditions, but you try somehow to avoid them. You always want to be in the safe state. Right?
Oh, so yes, this is about the safe state and bankers algorithm
Yes. Why bankers?
because of the analogy is used in the book.
Okay. What is the analogy?
Well, with the banker that gives some credit and assumes that no creditor
Mhm.
would need all the money at once, so it actually has less than money than all
Mhm.
of them need. And
Yeah, so I just want you also to have these, how is called, associative connections in your memory. Like, why is it bankers? Because it avoids the condition when all of the creditors get back and, not the creditors, the debitors. The debitors want their money back. So the bankers algorithm that they describe in the book is like perfect one, because in the real world, the banks don't work this way. Maybe you know, maybe you don't. So they have some percentage of the capital that is reserved for the credits, but they never expect to return all the credits at once. If they do, they would get defaulted. So just this is just a notion that the perfect bank should be like this, but in real world it's not. But we know what is the banker's algorithm, and it allows us to avoid this. Avoid this. How? So every process that requires resources, it needs us to tell how much resources in total it would need. So your process or the entity needs to know how many resources it needs to complete in advance. Then all of these. So how can we do this? Like we are programmers, software engineers. We want to implement this system. So maybe we need some kind of not contracts, but predefined API. So we have like maybe a working pool. So we have an environment in which we allow processes to execute. And to comply to this API, to be allowed to run in this environment, the process, for example, may be required to, before entering this environment, stating how many resources it would need in total, for example. So we can implement as an API, maybe as a framework for some language, right? Does it make sense? I mean, on the programming level, like in general, it is understood, right? So we need to know how many resources it will require to finish, but how to do this? For example, maybe you say, I have the predefined structure that I need to fill. And then with the structure, I say, I want to join the region, the safe state, not the safe state, the environment of the execution. And if there isn't some monitor, not the monitor, but the referee, the system that sits on top of this environment and says, okay, you with this state, with this required resources you want to join, we can allow you to join because we know the system will be still in the safe state and we can allow these processes to run in parallel mode. Okay, so there should be something that monitors and checks, and so it allows you. It doesn't say I will preempt you, I will hold and wait, whatever. No, you just do whatever you want. But we, before entering you in this environment, we check what you can do, what you will do, and if it still will leave the system, this environment in the safe state. Okay, seems to be making sense. The fourth one. Prevention. What do we remember about prevention?
well, there's several. We can break some of the constraints, not constraints, but required conditions for the deadlock to occur. So if we break it, then we prevent it, so it can never happen.
Yes, given that these four are the required and necessary and satisfactory conditions, all of them at once.
I don't think they're necessary because like
These
sometimes you
are the
can,
necessary conditions to get a deadlock. All of them, four of them.
yeah, they're all necessary but not sufficient. So like yeah, you don't always get deadlock when you get this, right?
Yes. So these are okay. I got what you're saying. If all of these four can hold at the same time, we can get a deadlock. We will not necessarily get it, but this is the system in which it can occur. Okay. So the prevention. How can we prevent mutual exclusion, for example? It was also mentioned in Tenenbaum.
Pooling of the resources.
Pooling of the resources. What do you mean pooling of the resources? Can you explain, maybe a bit elaborate on this?
Well, for example, to move some computation out of the processor.
Okay.
Well, we can give some process an ownership of the resource and say that all the operations are now should be done using through that process. So we just send a request and it does it.
So previously it
This is-
was like this. Yes, you're correct. So we had several processes, and only one of them could be in the critical region, right? For example, while they all wanted to do this. With spooling, we say there is only one process that will always be in this critical condition. Not a critical condition, it's not even as critical now. So we just say we offload our task to it, and we never get to this critical state. So with this pooling, for example, it was also correct if we have processes, and previously all of them wanted to work with the printer. Okay, we're always getting back to the printer, but they work with the printer. Now we say there is a daemon, the driver, that not the driver, the daemon, the other single process that works with the printers, and it decides which goes next. So it can avoid and prevent the deadlock on the mutex condition. Make sense to all of you? So
So
if
can
you,
you explain once more what is spooling?
Hmm?
So can you explain once more what is spooling?
I thought you would tell me what is spooling.
No, you explained like in different words and
Okay, spooling in our case, with the printers example, it is an idea if there is a slow job, slow task, like printing. So printers are very slow, CPU is very fast. You have processes that are run on the CPU, and one way you can say, okay, every time the printer has printed the buffer, we want to schedule the process that wanted to print. We wanted to schedule it again, so the process can be able to write to the buffer again. It would require you a lot of interrupts and a lot of downtimes. Not the downtimes, but the slow, the decrease, yes. So the CPU utilization will be decreased. So to avoid this, you say the fast processes can offload their task. So if a process wanted to print something, you say, okay, put a file to /var /var/spool, I guess, something like this. So if you put a file there, the file will be printed sometime. And there's one process that manages the printing, only it. So this is spooling. When you upload something to be done later, like a queue, you can think of it as a queue.
okay, thank you.
But sorry, but can be there a problem, like for example, we have a lot of fast processes and like one big process, and like one big process can maybe may not be executed because of a lot of fast processes and like for example like fast schedule algorithm. And like in this case, like our big document will not be printed because of too many small documents which are provided by small processes. Like that's the
Point
problem.
And this is a good point. This is the point that leads to the definition of starvation. And again, with the printers and the scanners. But in your case, if there's one entity that handles the queue, like the incoming queue of the files that needs to be printed, it is the charge of this single entity that will decide what to print. And if you code this entity in the correct way, there will be no starvation. But if this entity always gives the privilege of running to smaller processes, then there is starvation.
Okay, thank you.
This mixed be the starvation with the scheduling problem, and the thing that where is the one thing that tries to prevent the deadlock by having no mutual exclusion. Okay. Okay. Mutual exclusion, we prevent it. What is hold and wait prevention? There's a very trivial example with the Dynian philosopher's problem. You remember Dynian philosopher's problem? What was the problem?
We have 5 philosophers and they have 5 philosophers. And at any moment, the 5 philosophers can be in one of 2 states, either eating, either thinking. To eat spaghetti, philosopher needs to take both forks, one from left and one from right. And then philosopher finishes eating, he puts both forks on the table.
So the problem with the philosophers was that if a philosopher takes one fork, they do not put the fork back until they eat. So this problem means if you try to acquire a resource, you try to acquire the second one that you needed to finish. If you fail to acquire the second one, release all that you previously acquired. So you do not hold and wait. You hold. If you cannot hold the second one to finish, you put all of them back. So it's like try set lock. So you try to set lock. If you fail, then you fail. You don't wait for this lock in busy waiting. Make sense? Just say yes.
Yes.
Nice. Okay, really, does it make sense how you can prevent hold and wait conditions? So you program your system in such a way that you say, okay, I try to set a lock. If I failed, I just go to sleep. I do something. I don't do the busy waiting. I don't wait with this resource acquired.
But in environment, in the mistaken, the process releases all the resources at all times and tries to acquire all of them and one.
Yeah, so the point is you either acquire all of them or you release. So you don't acquire a part of them. So the problem is you acquired the process, you acquired something, so the others cannot use it if you have non-preemption and mutual exclusion. So you acquired it, but you're still unable to finish. So you will not release it. So this is why you either try to acquire everything and run, or you don't acquire anything. Okay, seems to be also.
About preemption, the second way to resolve it is to make, for example, in case of this, we can make three documents.
Yes, hold and wait or mutual exclusion. Yes, mutual exclusion. Also, you can sometimes you can make the data read only. So yes, there will be no mutual exclusion. So mutex covered, hold and wait covered, non-preemption. So how can we solve non-preemption? We can preempt, right? So we can try to take resources from the PC, or sorry, from the process. How can this be done? For example, any example from you guys? How can we preempt a process, preempt a resource?
Maybe we can try to kill a process and take its resources.
In the worst case, yes. But this is, I mean, about the preemption of the resources. So you were given some resource, and then it is said, okay, we take it back from you. For example, maybe your process worked with the network card. For example, it was working with the network card, and this process was reading all the packets and sending packets. And this process, and then some other process wanted to use the network card. We can just put to sleep the previous process. So the previous process, it doesn't even know that it was preempted. It just puts him to sleep. So now the resource is freed and the others can use it. So we need to schedule somebody who can preempt, who can take resources from this party and get it to that party. Does it make sense with the network card?
Yes, but it will not work with printers. Yeah, because like
yes,
it will be mixed.
Yes, otherwise you will just print several different arguments. You will have the race condition, by the way, when you print and use the same resources with the processes that are not synchronized. So non-preemption means that there is some third party, the powerful party that can take resources. So we don't kill, we just take resource. Maybe a resource can be maybe CPU time. So you say, I take this resource from this party and give it to that party. Okay. And the fourth is the circular wave. This is a very interesting part. So how can we detect a circular wave?
Detect or also to break this condition.
Not to break, first to detect.
You can construct resource request graph.
So, yes, so we need to create this graph. Who wants what, right?
And who owns what.
And who owns what, correct. Like this. These are just arrows and dots. Yes. we should always say trivial. So we need to understand the notion of the ownership. Maybe you worked with the languages that has this notion of ownership. Maybe something like Rust. Exactly. So there are languages that introduce these very interesting concepts of ownership. So when you try to be a very low level language, so you want to be very, very performant, and you cannot allow the garbage collection when you do the stop the world. Of course, there are other garbage collectors, but the point is, if you have this idea of the graph, who owns what, so they can be, for example, a strong reference and a weak reference, or whether you increment or decrement the reference counter. So when you have this graph, and then there are several fast graph traverse algorithms that can try to detect a loop. And if there is a loop in this ownership, in this dependent, we may have a circular weight. Make sense? For example, in Russian companies, there is a thing called like circular LTDs. So if there is a company that owns a company that owns a company that owns a company, there is something bad going on, because in this case, they can do the lens and they can get credits, and nobody will ever be responsible for them, because one company is responsible, the other company is responsible for that company, and so on and so forth. This is bad. So this is it is possible, yes. But they will get punished, but it is possible still. Yeah. So the circular weight. How can we prevent circular weight?
You can facilitate
Avoiding interrupts.
more than one resource.
Sorry, can you please repeat?
Disable interrupts.
What? How? How can it help? Okay, how can it help?
Disable interrupt solves everything, right?
Among the problems it brings. Yeah, this is okay. Okay, no, really. How can we prevent? So, okay, we can detect. We can build this dependency graph. We can file the loop. How can we prevent circular weight?
You can duplicate the process to hold more than one resource at a time.
Okay, this one holds one at a time. This one. One at a time. This one holds one resource. A
We
resource.
can enumerate resources and give some process a resource with greater number than all of the previously acquired.
I think there will be corner cases that will not satisfy,
There
but
will be no loop. There will be no loop then.
okay, can we say that, for example, if we still, so we can try to think like this. So we always have the tool that we detect, right? Not always, but if we introduce the tool, like the dependency graph, at any point when the process wants to acquire a resource, we can check whether there will be a loop in this graph. So if we always have this, so the point is, yeah, so we always need to know how to do this. We always need to know how to detect a circular weight. But if we don't let the system run, and then once at a time we check, is there a loop in this dependency graph? But if at the point of allocation, if we check if there is now a loop in this graph, so it's like a precondition. So when the process wants to acquire a resource, we say, okay, I check the dependency graph. If now there is a loop, so you will not allow it to do this allocation. So we return -1. So the point is that you do this in the precondition, and given that this precondition must always hold for resource to be allocated, to say we prevented circular loops. But this works in the system that when you can absorb everything. Remember, we talked about the distributed systems where you cannot see everything. So this is an interesting point. Right. So we did the recap, I guess. Okay. Consider the following state of a system with 4 processes and 5 types of resources. You considered already? Okay. Using the deadlock detection algorithm described in 6.4.2, which is it? Deadlock detection. show that there is a deadlock in the system. Identify the processes that are deadlocked. So what are these? What are these? These are the resources. Resources. These are the currents.
Isn't it request?
It's the right matrix, like it's not resources, it's requests.
Or these are the currents. Yeah, so with
Current allocation requests.
Right. Yeah, right. Now it makes sense. So we have the processes and the resources. Which one is the current? Which one is the overall? You know what are these letters?
E
Yes.
for exist and A for available.
Available and total. Yes, no?
Yes, yes.
Yes.
So can we identify the processes that are deadlocked?
Yes, A and D. P1 and P4.
This one and this one. How you do this calculation so quickly?
So firstly, I gave resources to P2, and then I give resources to P3, and then I see that I have not enough resources for P1 and P4.
So here's the solution. So can we try to guess the computational, not to guess, but to calculate and explain the computational complexity for this kind of algorithms? So, okay, if this is a very short example, like 4 rows, you can try to, okay, I gave this one, give that one, try this and that, so you can do all the permutations. But if there is a bigger algorithm, can we consider what will be the computational complexity given there is a hint, there will be dealt with the number of resources and the number of processes.
Something like this for example.
Yeah, exactly. So there will be the second part. Once again, you have the number of resources and the number of processes. So the computational complexity of these n times m squared.
What's the
The number of resources and the number of processes.
Okay, what's the number of processes?
M.
M, okay.
And m
Why
squared.
rotation, please?
Did they?
What's
Okay,
the-
okay, never mind.
M resources and
Or of resources, processes. Okay, so how we do this? We check if we give all of the required resources in the request to a single process, if it can complete and release the resources, will everybody else will be able. So is there a safe state or not? Correct? Because we defined the safe state is a state in which there is such a sequence of allocations and executions of the processes that each of them, all of them will complete. Right? Right. Okay. So I guess we've covered this as well during the explanation. Shall we go through this one more time? Just say no.
Yes.
Already covered. No.
Make a poll.
No. Oh, make a float.
A poll. Poll.
Okay, so briefly, the system can recover from deadlock in previous problems using recovery through preemption when we take a resource from a process. So we say that you go to sleep, we take your resource, we will give it to you back. So you are not killed. The second, the rollback, like in transaction. So there is a state, there is a snapshot to which you can safely roll back. And killing the process, you just kill, so all of its resources are free. So. Okay, this one is interesting. Can a system be in a state that is neither deadlocked nor safe?
live loop.
Live is a great example, yes. Yes. So there can be a state in which there is an example, but I think you want. Do we need to go through this exercise? Like, the problem is that you may know whether you will be deadlocked or not, especially if you do not know what is the number of the resources that the process will acquire. So let's go through the example. An example, we have 4 resources. We have 3 tapes. Okay, 2 plotters, 4 scanners, 2 CD-ROMs, and 3 processes competing for them. So if we have these, what it has, right? This is C, this is request, this is the available. So are we in a safe state? Let's start with an A. So it has 2, needs 1, available 0. So for resource 1, we already cannot start. For the B, it has 1, it needs this much. Can it continue?
No.
No. The C needs 1 and 1. It cannot continue, right? So it seems like we are in deadlock. Are we?
No, that is an issue.
Huh?
No, they're not in a deadlock situation. Deadlock is a state when the process is waiting for event for other work process.
Okay.
And here, you just cannot satisfy the requirements.
Yes. And the point is, if some of them, or is there any other process that can give us just one plotter, this one will finish, releasing this one, so it will be here, this one will finish as well, and then this one will be finished. So there is a possible thing that there is neither safe state nor deadlock. Oops. If a system has 2 processes, so there are like 2 processes, and 3 identical resources. Each process needs a maximum of 2 resources. Is that deadlock possible?
No.
No. Pigeonhole principle, exactly. So if you have 3 resources and you have 2 processes, each of them needs at most 2. So there will always be a case when if you have no hold and wait for some, even if you have hold and wait, the one resource will try to either pick one resource and hold. There will be 2 resources left, so the other one finish. Or you pick 2 resources and you finish, and then it's okay. Right? Okay.
So we can ask a question. For example, if you have a scaling algorithm, and like in this case, like our scaling algorithm will depend only on like like the amount of process which you want to assign. Like for example, we want to finish the first process, then to finish the second process. In this case, like our scale algorithm, like will be preempted by our own usage. Is it correct?
Can you please once again? So we have a scheduling algorithm. In this is a problem.
Yeah. For example, we have like a scale algorithm, like choose the shortest process to be executed right now, and like, but for our purposes, we cannot use like any algorithm because it depends on the like it depends like another algorithm, because how to say it right, like. Okay, for example, we need to finish processes in order. Yeah, we need to execute them in order. But like any scheduling algorithm will not work in this case, because like we need to just to execute like our basic algorithm.
So if you have this notion of executing something in order, it already implies that you have some notion of scheduling, no?
Yeah, but like what our general algorithms like choose the shortest process to be executed will not work in this case. Yeah, we just need to replace all of them by such algorithm as we invented here.
Most likely, yes. We just
okay. Thank you.
Yeah, but you need to remember that we have no such notion as the shortest process. Remember, usually in our system we don't know what is the shortest process. We have shortest stop in the batch systems, but in interactive systems we don't have the shortest process. We can try to estimate, but this is a bit different part.
Okay, thank you.
Yes. So finally, we need to derive some formula. Consider the previous problem again, but now we have P processes, each needing a maximum of M resources, and we have R resources available. What is the formula? Like, what condition must hold to make the system deadlock free? So R should be something of greater than or equal.
Oh,
So we have, remember, we had two processes and three resources. And okay, there is a spoiler. Violetta, it should be what is the condition?
R should be this number or greater.
Okay. Like this. Can you please
Yes.
explain why?
Yes, imagine the situation when every process has all except one resources that it needs. And in order for that lock not to occur, we should have one extra resource to be able to terminate one of them and to get resources back.
Great. Is it understood? So in the previous part, we had three resources and we had two processes that wanted two resources. Right? So we have the number of resources anyway bigger than the number the one process wants. Correct? But we also need to have them to be, for the system to be deadlock free. We always need to have the situation that we have one extra resource. So if every previous process acquired the resources, there is still one more resource for at least one of them to finish, to release the resources, so everybody else can continue. Like in this case, we have two processes. One picks one resource and holds, the other picks one resource and holds. There is still one resource, so at least one of them will be able to finish and to release the resources.
So just if we have enough resources, we're not going to have any deadlocks at all.
No, for the deadlocks, you always need to refer to the previously mentioned four conditions. And then you need to think whether you want to do nothing with the deadlock and you don't care about these conditions, or you say, I will try to detect the deadlock and then prevent somehow, or I will try to avoid using some, but in this case, you need to do some dynamic resource allocation and to understand whether this is a safe state, not safe state, unsafe state, or you prevent by attacking one of these conditions. So if you have multiple resources,
any program is going to be deadlock free, right?
No. I mean, if you have too many resources, it means that one of the conditions may be not needed. So if you have multiple resources, too many resources, and too few processes, of course, but you cannot say how many processes you have, right? So the point is to build such a system that we don't know what is the number of processes. We don't know. There may be too many of them, too few of them, we don't know. But we need to make such a general system that given no matter how many processes will be still deadlock free. Because if you can say that, you say, if there are too many resources, how much is too many? We don't know, right? So with any number of resources, we need to understand what are these conditions and how to tackle them.
Okay, clear. Thanks.
Sorry, could you please go back to previous problem solution, like this ABC processes? No, not this one, sorry. Yes, stop. Next slide. Why is the state is not deadlocked? Like, because I still don't get, for example, if A requests, like, what is it? It's like,
yes. The point is, if you always request all of the resources up front, then there's a deadlock. But if we say that A, sorry, what is it said? If A, it needs these many resources. If it needs them all at once to finish, then there is a deadlock. If we always consider allocation of resources all at once. But it needs, for example, two plotters. We have two of them available. What if we can use these two plotters and return them back. And now we will need of 0 plotters. You see? And the same can go to all the other resources.
I get, thank you so much. Like you just assumed, yeah. Thank you so much. I got.
So the question is, you need to understand what are the possible outcomes. Okay, you say, for example, on the written, you say, if you're given this exercise, if we request all the resources at once, then there's a deadlock by definition. So you say here, here, here. But if you want to show that you have read the book, you say, okay, but if this program can only use a small portion of the resources it needs, and then to finish one of the procedures or one routines and release the other resources, then they're neither safe nor unsafe, nor deadlock.
Thank you. Okay.
Yeah, so we've already covered for the bankers algorithm, there is the matrix, there's number of processes. So you go through the matrix, so it is m times n, and by the number of processes. So for every process, we check the whole matrix. For every process, we check the whole matrix. So the time complexity would be m times n, where the n is the number of processes, and m is the number of resources. Correct? Correct? A bit slower, shall we repeat? Okay. Maybe. Once again, we have a matrix, right, in the bankers algorithm. It is of size n times m. So these are the processes, these are resources. For every of them, we need to check if we take this algorithm to finish. We need to check if this one is finished, will any of them finish? If this one is finished, will the rest of them finish? And so on and so forth. So you take one, you check almost the end. So this is the big O notation. So this is not the exact case, but this is the big O notation. And you check. You removed one, you check almost all of them. You remove the second, you check almost all of them, and you go into the deep. So when you say we check this one, we still n-1 to check. And for each of them, we also need to check the previous ones. And then you repeat this and you start with the second row. So this is why we have m times n times n. This is the big O notation. Is it clear for you? Yes. Okay, what is the smallest value of x in which this is a safe state? Nikita has left the chat. Okay, spoiler alert. This is a very, very likely question, kind of question to be in the exam. Like for 2 previous years, we kind of had this. Kind of the same question, but okay. Okay, Zahar said 1. If this is 1, then what? Then we can run process D. This one? Yeah. So it's required. This is the maximum. Can we? Process D. So the maximum is we need 2 here.
Yeah.
And 1 here. So
yes, 1, 1, 1.
And we already have this one, so we finish with D.
Yeah, we finish with D.
Then we give it back.
1, 1, 2, 2, 1.
The problem is this thing needs 3. No way you can get this 3. And this one needs 3. If you sum all of that allocated. So the point is, so the smallest value will be 2. I guess we can check this in the solutions. These are the arithmetics. We still have a few times left. A few minutes left. So briefly, we've discovered and we covered and we talked about deadlocks, right? So what are deadlocks? This is the system where neither of the processes can finish, so they are all waiting. What is a live lock?
So live lock is a situation when you have a policy that if process cannot allocate resource, it frees all the resource it already holds and try to allocate them again one. But they can have a situation with the process. If we will perform these actions simultaneously, then we will lock again and again.
Yes.
We
So a live lock is like when you open the door and you want to let the person that is in front of you to let to come, and you don't know who wants to come first. So you both try to go and now you revert. So you try to go and you revert. With the cars, so two cars are standing on the one-lane bridge and all of them saying, okay, you go first. And then they don't understand who should go first. And they are not deadlocked. They have the resource. The resource is free. They can acquire, they can use, they can finish, but they don't. So how do we handle live locks?
I'm not sure how it's supposed to be, but I would add some randomness to the decision.
First of all, yes. Second, it is said in the Tannenbaum that we don't handle that live locks because it is too unlikely to appear. Okay.
Sorry, but like, does live lock exist only in true parallelism system? Like when you have like some amount of cores or some amount of CPUs, it doesn't work for one single process.
Yeah.
One single CPU. Sorry.
Consider the distributed system once. So okay, in true parallelism, yes, makes sense.
Okay, thank you.
So this is why in Tannenbaum it said that we don't care about live logs because they are very unlikely to appear. And if they appear, okay, they go back, then some random time will happen, some random interrupt. So this thing will very unlikely to happen again. But in theory, it is possible, especially in our human theory, like when we stand on and try to let the other person go through the door and stuff like this. The starvation, as we said, this is the problem when actually there is a resource and the process can be executed. But for some reason, for example, for bad and poor scheduling, it is never scheduled. Right? This is the starvation. Okay. So in order to control traffic, a network router theoretically sends, so this is the the network stuff. What is this kind of deadlocks? Or not the deadlocks, but special conditions. What are they called? When we're not talking about the resource, but the information. Yes, this is communication deadlock. So this is not even deadlock, but this is the problem of communication. Let us say it this way. So this would be a special case, right? So the point is, if there are two processes, simply not in this problem, there are two processes, and one sends the message to the second one and waits for the response. And for some reason, it doesn't know that the message didn't come through, so the cable was broken. So it sent and waits, and the second one cannot respond to something that hadn't arrived to them. So they are not deadlocked, but they are waiting because they have this communication deadlock. The communication is broken, so technically they can run, they can work, but there is something that they don't know about and they cannot know about it. Right? So for those of you who have worked with networks, I'm more than sure that you have seen always have seen this thing that is used to avoid these deadlocks. Timeouts, yes. So you set a timeout. So if you sent a message and it didn't get back, you say, either I will get back or in 60 seconds, I will repeat. I will do something else. So this is one of the cases. So you say the timeout is a kind of a solution for the communication deadlock. So you will not wait forever. You will revert, maybe do something else, handle the error and so on. Nice. Guys? Clear?
Can you return to the previous problem with value x?
This is just a computational problem.
Yes, but we have like, if we put 2,
So you see, if we finished and here is 2,
Get like available 1. How
What?
do we?
sorry,
Here you have available 1 in the first resource.
once again, so the process A,
So for example, we put 2 in X.
mhm,
So then we will get rid of process D, and then we will have like 1, 1.
let's draw. So if X is 1,
Ah, yes, thank you, sure. Thank you.
So
And after that, we will get all the resources from it.
mhm,
can you go back to this problem again? Statement. Yes. So, like in system, we have only 2 resources of type 5.
no, we have 1 available, 1 here and 1 here.
Um,
So it needs maximum
No.
of 3. It already has 1. The other process has 1. It is available 1. It's some 3.
What? No.
Once again, it needs 3. It already has 1.
Yeah.
There is free 1 resource
Oh, yeah.
available, and 1 is holding here. So in,
Why it's holding? Yeah. It's not holding.
ah, sorry.
In Tannenbaum, they provide a formula that number of resources in the system equals to number in available vector plus number plus
Yes,
sum of
correct,
corresponding columns.
correct.
So there's a problem.
Allocate 1.
Yeah.
So one of them will not be able to finish at all. And this is the process A, right?
Yeah.
Mm-hmm.
But where is
Okay.
the typo?
Yes. I even remember there was a typo in Tannenbaum, so it happens. Yes, I also wanted to talk about the distributed resources, but we are run out of time a bit. So briefly, we have several machines doing it right. And this is a system of several machines. They talk to each other, they acquire some resources, maybe a database connection, whatever. And there's an interesting problem. So how can you detect if there is a deadlock in the system if you cannot see every individual machine? So you don't have the one system where you can see all of the processes, all of the resources, but you just know that someone requested resource from here. The other one requested resource from here. This one requested resource from here. So you don't know. There are too many requests, too many processes. So briefly, one of the ideas that you may have seen in the Kahoot, it was called, what was it called? It was called Shandi Misra gas algorithm. So the point is, they have this network, and in this network, they send a probe message. So this one sends probe to everybody else. And it has 3 parameters, like who sent, to what resource, to whom it sent. So all of them then redistribute this message, but they change the from who wanted this resource. And the point is, if there is a loop in the system such that, so you sent a probe with these params, and for some reason, the same message gets to you, the message that you have sent gets to you, there is a loop in the system and there is maybe deadlock. Okay? And there are other 2 things that I encourage you to check, but not enough time. These are weight die. So you there are several processes, either there's an old process and the young process. And either when the young process wants to get the resources from the old one, the young one dies. And there is the wait and wound, when instead of killing the young resource, for example, it was a transaction, just say you wait, you go to sleep, and then you let the older one continue, and so on. I will just now. Yeah. Just for your curiosity, if you want to check, this is somewhat short PDF in 17 pages about the distributed deadlocks. Okay. So, do you have any questions?
Will we have questions on distributed deadlocks?
No.
Okay.
but I encourage you to cover them because you can have them on your job interview. If you're going to work with some cloud systems, backend development, blah blah blah, it is a very good question to ask. Because you can formulate the problem in such a way. You say you have a cluster of n machines and they talk to each other and they want to acquire the connection to the database. And what can go wrong? And so you're trying to see if the interviewee sees and knows the distributed deadlocks problem and the approaches to solve them. So you now may have seen that I talked to you from my perspective of a backend engineer. Okay, if there are no problems, that there is almost no time was.
I have a question.
Okay.
People taking an alternative form of written exam,